Doug, Stand-Up Physicist. Today I want to give you a sense of what a scientific meeting is like. Because most of you probably haven't gone to one. Well, it's kind of like most any other meeting. They usually happen at a university or for bigger conventions at a hotel. And there are a bunch of different sessions that you can go to. And for the ones that I end up attending, they often break down to groups that only have, say, 10 or 20 different people in them. See, because I go to those talks where the people volunteer to speak. They're not invited by the people organizing. And so this is kind of the small lecture circuit. It's kind of like playing at a rock club on a Tuesday night, where the only folks that show up are the people in the band and maybe one of their really close friends. You know, we're not playing the Symmetry. Why don't we just say that much? So I go to these meetings and they're very helpful to me, mostly in the preparation. Most of your time is not spent at a lectern like this. Instead, you spend most of your time in the back row. Well, maybe I should say that's where I spend my time. This actually goes back to 8th grade. It may seem hard to believe, but when I was in school, I enjoyed making fun of the teacher and my fellow students and just about everything else. And in my math class, I did very well. As a matter of fact, in the final quarter, I averaged, I think, 102 because they gave extra bonus points and I also got those right. But they gave an award at the end that was for the best student who was also a good little doobie. And I didn't get the award. My father actually wrote a protest letter. I still didn't get the award because I made too many snide remarks. And so now what I do is I always sit in the last row so I can still make my snide remarks without bothering anybody. At scientific meetings like this, it's really hard to understand what anybody else is saying. This isn't just for my talks. This is an observation I have of other people, because the fields are so technical that it takes a long time to really understand what's going on in general and then what's going on very specifically. And you only have like 10 or 15 minutes to explain something that's going on this very specific level. And that's very hard to communicate. So the only folks who generally can ask questions are people who work in an area very, very similar to the one that's being presented. And then because they work in the same area, they can ask a good question. I actually consider it a little challenge to myself to see if I can listen well enough to ask a good question. And so I often take notes, which I never go back to and refer to because, you know, these topics aren't what I do. But, you know, I take my good notes and try and see if I can come up with a good question. So you go through 3, 4 of these an hour, and after a while, they're kind enough to give you a break. So you get up and, well, you learn to mill about. And that's kind of a challenge at a meeting like this. Usually what people do is 2 or 3 people from the same research group will go to the lecture. And that helps a lot because you can just hang out with your close friends. Or, since they've gone from undergraduate to graduate to postdoc to maybe even a professorship at different universities, they might actually know people. They might have gone to a bar with somebody. Now, a person like myself, I haven't done that. So what do? Well, I spend a lot of time milling about. And it seems like people who just don't know anybody else seem to find those other people. And they hang out together and say things like, gee, isn't it hard to socialize? And that makes it, the coffee breaks a little bit more enjoyable. But then you have to go back and listen to a few more. And of course, I'm just looking down lists and saying, when do I show up? Well, I usually get a time slot Saturday mornings because that's when, you know, the really off Broadway sort of talks happen. And my time comes up and you've got to scurry up to the front of the room. This is a talk that I gave in Dallas at the American Physical Society. There were maybe 12 people in the room. 10 of them had given presentations, only 2 stragglers. One of them, the people in the room, was the person who ran the meeting. And when you run a meeting, the most important thing is to keep people on time. The reason is that any one of those speakers could probably talk for several hours on their topic without much problem, because they've been working on it for months and months, if not years. But they've only got 12 minutes, and so you've got to keep the time. Fortunately, that guy isn't here, so I can go over time. But I'll try not to. So the title of this talk is Unifying Gravity and Electromagnetism, a riddle you can solve. John Archibald Wheeler wrote this incredibly thick book on gravity. It's like a phone book, except it's full of very difficult math. And he had this to say about the next step in physics. How can physics live up to its true greatness except by a new revolution in outlook that dwarfs all its past revolutions? And when it comes, will we not say to each other, how beautiful it all is, how simple? How could we have missed it for so long? I think everybody who does research in how gravity works hopes this quote applies to their approach. So let me try and justify it for my own work. Newton's law of gravity is the simplest rank 0 field theory there is for gravity. And it's a very good theory. It's the one we use in powering rocket ships. Unless they have atomic clocks, if they are that fussy about time, they will realize that this law violates the principle that speed of light is a maximum. And that's a deadly flaw in that approach. So what's a better approach? The better approach is general relativity, because that is the simplest rank 2 field tensor there is for gravity. But there's a problem with that approach too. And that is when you try and quantize it into these things that are kind of wavy clumps of stuff. No one's been able to do that. for like 75 years, people have been trying. As smart people, they can't get it to work. So, my GEM proposal for gravity and EM is to form the simplest rank 1 field theory there is for gravity. So this is the Goldilocks approach. Between 0 and 2 is a rank 1 field theory. And that can respect the speed of light c and be quantizing. So how do you solve a riddle? Well, what you do is you start in a rock solid place. And then, for reasons that are justifiable but a little odd, you take a step in a direction you normally wouldn't take. And then for another very valid reason, you take another step, and suddenly you're looking in an awkward direction. And yet you know why you're here. Now you're not comfortable with this solution, but that's okay. That's the nature of a really good riddle. So how am I going to start with a really solid place for unifying gravity and electromagnetism? Because we don't have a unification. I'm going to start from the best place I can, which is the best theory for gravity combined with the best theory for how light works. And that would be with the Hilbert-Maxwell action. That has this R, which is the Ricci scalar that's going to do the work of gravity, and that anti-symmetric tensor that's going to do the work of EM. Now, what do you do with an action? Well, an action is everything that can happen inside of a volume. And what you do is you vary one of those fields to generate the field equations. So, if you vary the metric, then you end up with Einstein's equations for gravity. If you vary the potential, you end up with Maxwell's equations for EM. But there's another perspective you can have on these equations, and that is with group theory. Because what group theory does is it allows you to see some symmetry in the action. What that means is I can change this, and yet the action stays the same. And if you can change something with the action staying the same, you have found something that's going to be conserved. Now, the group theory approach to gravity is not very well taught. In matter of fact, it has to do with this group Diffem, a group of Diffeomorphisms, and Wheeler's book doesn't even have that in the index. So I'm going to try and introduce you to this by showing you examples of this particular group. And this is all smooth coordinate transformations. Well, what does that mean? That means you start out with a metric like this that applies in completely empty spacetime. And you take small steps away from that. The first step away is to add a term in that upper corner, and that's essentially a way to write Newton's law of gravity. Now, if you want to write something that is an approximation of Einstein's approach to gravity, you have to add in a few more terms. And the thing is that these terms are the ones that are tested in experimental tests of general relativity. But it doesn't have to just be a solution to the Einstein equations. It could in fact be a different metric, just as long as it has these same 5 terms, and the one that I work with is known as the Rosen metric. But if you now say, now let's go to the next level, have we tested that? We haven't. I in fact went to a meeting once just to ask an expert in the field, Clifford Will, when were they going to get around to measuring those terms? Because when they get those terms, I will know whether my proposal is right or it is wrong. I can reject it on experimental grounds if they go and measure those. And Clifford Will made very clear he didn't know when that was going to be measured. I don't think that completely gets the idea of this group, though. We've seen different members of the group, but the idea is more about geometry. That the geometry is not set by the way you're doing physics. Sean Carroll had this to say: it is possible that two purportedly distinct configurations of matter and metric in general relativity are actually the same, related by a diffeomorphism. You might at first think, well, that means that I start out with, say, Euclidean coordinates, x, y, and z, and then I go over to spherical coordinates, r, theta, and, like a ball. But that's actually not quite the issue, because something like classical physics works in either one of these coordinate systems. But classical physics says time can't rotate into space, like ever. And in special relativity, that works fine, switching between coordinates. But there again, you say, oh, everybody has to be an inertial observer. So it's more that you can actually change the very metric that you're using, and it's okay, it still works out. So let me give you an example of this. We've got this box squared A, and most physicists, if you show them that sort of equation, they'll raise their hand and say they know the answer. The answer they know is that the potential must be a charge over R. And that is an answer so long as the metric there is constant and the connection ends up being 0. The reason is because that box squared is really for two covariant derivatives, which has a divergence, the differential operator and a connection, differential operator and a connection. And so if the connection there is always 0, that's an answer. But it's possible to end up with a totally different situation where your potential is actually really boring. It's constant. So this two derivatives of that just don't do anything interesting. And instead you have you're taking the divergence of a connection. And I'll get to that at the end of my talk. That we can see in this situation, we've got two genuinely different metrics explaining exactly the same thing, a static point charge. So I've spent this time trying to educate you about the group Diffeom and how it relates to gravity. The group that governs electromagnetism is known as U1. And it really arises because the antisymmetric tensor there has zeros going down the diagonal. And one of the consequences of that is in my covariant derivative that has both a differential and a connection. Well, since the connection is symmetric, it gets subtracted away. It goes away. It's not there anymore. We're on slide 9 of 12. We're almost done. So where's that first step I'm going to take in an odd direction? Well, our effort to quantize gravity has been going on since 1930. And who's tried to do this? Well, Einstein was certainly the first. Dirac gave it a try, and Feynman tried, and Weinberg tried, and Hawking tried. Very bright people. And they've all failed. So to me, that's a message. And the message is this: it can't be done. And so, since it can't be done, eliminate it from the metric. And now we have the Maxwell action. We drop the R, because the R is essentially the way to implement the diff-m symmetry. I didn't eliminate the diff-m symmetry. That's what gravity is about. But by eliminating the r, I'm also eliminating Einstein's field equations. That's going to make some people in our audience very uncomfortable. But I think it's something we have to do to get along with quantum mechanics. Now, what are we left with? Well, we're left with Maxwell's action. And this is a problem, because the diff-m group is describing different metrics. I can use different combinations of metrics. And to change from one metric to another metric involves changing from one symmetric metric to another symmetric metric. And the difference between those is symmetric. And yet all I've got there is an anti-symmetric tensor. I can't describe it. It doesn't work. So what am I going to do so I can now describe the symmetric changes in a metric? I'm going to do more with less. I'm going to subtract some more and end up with the gravity and EM action. And what I have here now is an asymmetric tensor. Asymmetric tensors have an anti-symmetric tensor and a symmetric tensor. And together, they're asymmetric. But that symmetric tensor can now possibly describe how the metric changes. But it also causes a problem. I lose that U1 symmetry. I should say, well, in most situations I lose it. If it's massless, the U1 symmetry is back. It's perfect. But if there's a mass there, U1 symmetry is broken. Now it's broken a really little bit. By that, I mean if you measure the sizes of things, electric charge is like, is 16 orders of magnitude larger than mass charge measured in the same units. So yes, symmetry is broken, but ever so slightly. We don't get back Einstein's equations for gravity. And believe me, there will be people who are very upset with that. But we still have this four-dimensional wave equation. And we know one solution for that. That is, if you're in a flat space-time, you just use charge over r, and you're done. But there's something I call general Gauss's law, which is like Gauss's law, except it's also got a gravity part. Essentially, gravity just takes a little bit away from the charge part. And you can imagine a potential that's completely boring. It's constant. You take the derivatives of that, it's zero. Now everything has to come from the metric. And so the metric that I'm using is known as, well, this is a variation on the Rosen metric, but it's got these exponentials down the diagonal, and then it's got a charge over r. And what you need to do is calculate the connection for that particular metric. That kind of calculation can be a little scary, but I've made it easy. I've made it easy because it's static. And I've made it easy because it's diagonal. And so really only one of the three possible derivatives of the metric survives. And I've also made it an exponential, which means that you get back the exponential plus the derivative of the exponent. So amazingly enough, we end up basically with a Laplacian operator acting on a charge over r, just like we did before. And so the important thing here is to realize we are not fixed on a particular metric. We could have used a flat space-time metric and had a charge over r, or we could use this dynamic metric and solve for exactly the same physical situation. So the final riddle is, can this equation be quantized? Because that's the riddle that has stumped people for 75 years. And I think the odds are incredibly good that this can be quantized. Because we know how to quantize that four-dimensional wave when we only want to do EM. And when we do that, we use the Gupta method for quantization, and that has two modes of transmission for EM. But there are also two other modes that cause technical problems. There's a transverse mode and a longitudinal mode. And we have to, for a spin 1 field, say they are virtual. But if we try and do both gravity and EM together, then we have a spin 1 field to do the work of EM, where like charges repel. And we have a spin 2 field where like charges attract. And that will be the longitudinal and scalar modes. This also has an experimental prediction. And that is, if we ever are to detect a gravitational wave, this predicts that the modes of emission will be scalar and longitudinal, not transverse. General relativity says it should be transverse. So if we ever get that data, we might have another way to explain the difference. Another way to test this proposal and find out whether it's right or it's wrong. So what I've tried to do today is start out with the most solid approach to unifying gravity and electromagnetism we have. That would be the Hilbert-Maxwell action. And with a little bit of an eraser, end up with an action that can still do gravity and electromagnetism, but in a way that is going to be consistent with quantum mechanics and can be tested. Thank you very much. Any questions?
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
Excuse me, but how much is your theory like a duck? Because you got the wings to do the transverse wave, and then you got the bill and the tail to do the work of the longitudinal wave. So how much is your theory just like a duck?
I think that ducks are completely irrelevant.